Hello, in this demo, I'm going to give a quick walkthrough of the notebook Calculus for Deep Learning. In the first cell, I just import all the required libraries required for the further installation. Then here I define helper class in the next cell, a function called numerical derivative that approximates the derivative of any function using the central finite different formulas. Then next go to the back propagation. This is the most important cell in the notebook. It implements a complete neural network from scratch to solve the XOR problem. I define a simple neural network class with a Xavier initialization, a forward pass through sigmoid activation, and a full propagation method that computes gradient using the chain. Next cell is this cell defines a function f of xy is equal to yeah, this is the cell. This cell defines the function f of xy is equal to x squared plus 2xy, the formula that we see here, computes its partial derivative analytically. And together they form the gradient vector, the points in the direction of the steepest increase. Next cell, here I implement, yeah, here I implement the chain rule through a minimal two-layer network. Input goes through weight W1, then sigmoid activation, then W2. Yeah, here W1 and W2, and finally MSE loss. Next cell demonstrates the chain rule on concrete example, which is this equation, and I decompose it into an outer function and an inner function g, compute each local derivative separately, and then multiply together to get the dy dx. Next, this cell plots all major activation functions, sigmoid, tan h, and ReLU, alongside their derivative in a 2 by 3 grid. Derivatives are critical because they appear in a propagation chain rule. In the next cell, I visualize how single neuron's output changes as its weight varies from -2 to 2 for a fixed input. This is the simplest possible demonstration of how the derivative tells us which direction to move the weight. In the next cell, this cell demonstrates a 3D bowl-shaped loss surface and plots its counter map with gradient arrows, showing the direction of the steepest descent at various points. In the next cell, what is implemented is the cogradient descent algorithm as a reusable function. At each step, it computes the gradient of the loss, subtracts its scale by the learning rate from the current weights, and records the full history so optimization path can be visualized. In the next cell, we visualize the actual path taken by gradient descent on the counter plot and plots the lot decreasing over iterations. This is the this is the, we can see it in the output. In the last cell, we compare three learning rates side by side on the same loss surface. A too small rate makes tiny steps and coverage slowly. A just right rate converges smoothly, and a too large rate overshoots and can diverge, showing why learning rate tuning is so critical in training neural networks. So that's it for this notebook. Sorry. Thank you.